Today we're going to look at finding the modulus and the argument of a complex number, which will help us go from the rectangular form to the polar form of that complex number. So if we start with the complex number 4 plus 3i, and I'll draw that in, we'll call that z, so that's 4 plus 3i. We're going to write this as z equals r cis theta. This is the polar form. Cis is just shorthand for cos of the angle theta plus I times sine of the angle theta. And that can be thought of as the real and imaginary parts of the complex number. So instead of drawing it with rectangular coordinates, we're going to draw it as a number which is on the complex plane, and it has a length r and an angle theta. So this is written as relative to a pole, or the origin, hence the name polar as opposed to rectangular coordinates. So here's the same number, and you can see that the length of this side is 3 and the length of the bottom side is 4. So this can be drawn as a right angle triangle. And if we draw this triangle separately, you can see that if we call this side a and b, we can just use Pythagoras to say a squared plus b squared equals c squared. So a, the bottom side, will just be the real part, and b, the side on the right, will be the imaginary part. And c is what we called r, or the modulus of this complex number. I'll just put the e and the m in there so we can differentiate between real and modulus. So 4 squared plus 3 squared equals 25. So r has to equal the square root of 25, so it's 5. So the modulus of this complex number, 4 plus 3i, we can write that as 5 cis, and then we just have to work out what theta, or the argument, is. Often it's written arg for short. So coming back to this, if we draw this as a right angle triangle again, and we label the sides opposite and adjacent to the two sides we have, just remembering SOHCAHTOA, we're looking at the opposite and adjacent, so we'll be dealing with tan. So tan of the angle is going to equal the opposite over the adjacent. So the opposite will be the imaginary part, it will always be the imaginary part, and the adjacent will be the real part, so we can just write tan of the argument is equal to the imaginary part divided by the real part. So therefore the argument has to be the inverse tan of the imaginary over the real part, and you can jump to this step, you don't have to prove it every time. So our argument is going to be the inverse tan of 3 over 4. So that's 36.9 degrees, or thereabout, or if we're going to do it in radians, 0.635 radians. So we can write z equals 4 plus 3i in rectangular coordinates, or we could write it as z equals 5 cis 0.635 radians. Just a quick note, if I change my complex number to be negative 5 plus 3i, we'd draw it like this. And if you take the inverse tan of that, you're going to get negative 31 degrees, which, as you can see, isn't correct. Negative 31 degrees would be down in the bottom right. But if we add 180 degrees on, or a straight line, we can see that 149 is more like what we'd expect. So we needed to add on 180 degrees if it's in that top left quadrant. Here's the example from before, and if I just make both those numbers negative, so instead of being 4 plus 3i, we'll have negative 4 minus 3i. The original angle was 30 degrees. We got that from taking the inverse tan of 4 over 3. If we take our new complex number, negative 4 over negative 3, negative 4 divided by negative 3 is the same as 4 over 3. So inverse tan of negative 4 over negative 3 will still give us the same 30 degrees. but because it's just rotated by 180 degrees, if it's in that bottom left quadrant, we also need to add 180 degrees on. So I think that was 36 degrees, not 30. So the correct answer would be 216 degrees. So if it's in quadrant 2 or quadrant 3, you have to add on 180 degrees, or pi. Right, so quadrant 1 you just leave the same. Quadrant 2 and 3, you're going to have to add on 180 degrees. Why is this? Well, here is a graph that you might recognize. It is the tan graph. I've just drawn it there up until 360 degrees or 2 pi. There's 180 degrees, and I've just drawn a dotted line at 90 and 270 degrees. So there's your origin, or 0 degrees, and that's where quadrant 1, quadrant 2, and quadrant 3 would fit in. So quadrant 1 is 0 to 90 degrees. Then from 90 to 270 degrees you have quadrant 3. And quadrant 4, as you can see, is on the third iteration of the graph. So for example, if we had a number down here, like 6 and negative 2i, if you take the inverse tan of that, you're going to get a number negative 18 degrees. We're looking at a number that's closer to 360 degrees. So what that means is, we're looking for a number about 342 degrees. So if you're in the bottom right quadrant, because you always measure from 0, and then you always go anti-clockwise. If you're in the quadrant 2 or 3, you have to add on 180, but in quadrant 4 you have to add on 360 degrees. So that's plus pi in quadrant 2 or 3, or 2 pi in the fourth quadrant. So here's an example. We'll start with z equals negative 5 plus 2i. We're going to convert that to polar form. I'll start by drawing it on so I can see whereabouts my complex number is. So it's up here in quadrant 2. So we have to find r. Don't forget, you're going to have to add on 180 degrees because it's in quadrant 2. R squared equals the real number squared plus the imaginary part squared. So it's negative 5 squared plus 2 squared. So we'll just leave r as the square root of 29. Now we have to find the angle, or the argument. So it's going to be the inverse tan of the imaginary part divided by the real part. Right, in this case, it's going to give us negative 22 degrees. Don't forget to add on 180 because we're up in quadrant 2. So negative 22 plus 180. Our argument is going to be 158 degrees. Just writing that out as a proper answer. rcis theta. Right, let's just test that this works. So our polar form is is root 29 cis 158, dealing in degrees. Remember, cis just stands for cos of the angle plus I times sine of the angle. So that's root 29, and cos of 158 is negative 0.93, about. I've just rounded a little bit, plus I times 0.37. I'll just expand this out. Root 29 times 0.9, that's negative 5.008, and the imaginary part is going to be 1.99i. So as you can see, that's pretty close to the correct numbers, so this method worked.